Now, whenever we talk about anomaly detection, it basically means to detect outliers, right? Now, when we consider outlier as a very important parameter while solving a specific problem statement, that anomaly detection is the use case that you really need to focus on, right? Now, over here, I've just given you some examples, but let me just give you a small real world examples. Let's say, your bank account is over here. You are probably present in India right now. Now, if someone tries to use your user ID or your password or your phone number from a different location altogether, right? Let's say they want to use it from outside of India. Then suddenly you get a message from the bank saying that someone is trying to log in into their account. Not only that, your Gmail account and all. So how it is being able to determine that? It is very much simple. It is just considering that some outlier event is basically happening, some anomaly event that is basically happening. And usually when we talk in terms of security point of view, this is very crucial statement itself, right? Now, just to talk in a simple point of view with respect to an outlier, let's consider that I have two features like height and weight. Now, in this particular feature of height and weight, what we do over here is that all these are the data points, but this data points that we see over here, these are basically kind of outliers, right? Now, outliers can play a very important role for a specific problem statement, and it can also not play a very important role for some specific problem statement. Like, let's say that I want to detect whether the person is having cancer or not, right? So not every person will have a cancer, only some number of people will have a cancer. So in this case, this person who's having a cancer can be considered as an outlier, and it is very crucial for a specific problem statement, right? So similarly, wherever we are trying to predict or we are trying to find out that specific outlier that may be very important for a specific problem statement, that is where anomaly detection comes into picture. Okay, one more basic example with respect to bank account I've actually told. You may be also getting a scenario that for a specific I need to probably find out which all IPs from a list of IPs are basically a kind of a fake IP or hacking IP. Something it can happen. Let's say a hacker may come from some other kind of mediums, they may try to hack some kind of servers. So from what IP it is basically coming, can we find out that it is an anomaly or not? All those things we will be able to do it, right? Now in anomaly detection, again, understand we need to detect outliers, but this outlier can play a very important role. One more example I would like to give you, and recently I know everybody sees IPL, right? Indian Premier League. I think you are fond of cricket, okay? Now let's say in IPL there are 20 overs, okay? I just create a random data. In the first over, the team is scoring 15 runs. In the second over, the team is scoring, let's say 10 runs. In the third over, the team is scoring 12 runs. In the fourth over, let's say that I write by mistaken over here, the team is scoring 100 runs. Is it possible? It is not possible, right? Because see, in this case, maximum how many runs you can basically score in an over? It is 36, right? If something greater than 36 is coming, obviously, by using a different anomaly detection technique, I can actually be able to find out, yes, this is a specific outlier, or this is completely unique from all the other overs. So this kind of uniqueness, I really need to find out from a specific data, right? So in anomaly detection, we are going to see 2 to 3 types. Okay, the first type that I'm actually going to focus on is basically called as isolation forest. Okay, isolation forest. Now this isolation forest is again an anomaly detection technique, and internally over here you are going to use decision trees. Even though this is a unsupervised machine learning, but you are going to use the decision trees for some specific purpose. Now let's understand for what purpose you will be using it. Okay. Now let's consider that I have this F1, F2 feature, okay, and I have a lot of data points, something like this, or I'm just considering 2 features, or I can have multiple features over here, F3, F4, like this, okay. Now what does isolation forest basically say with respect to anomaly detection? This basically says that what we will do is that we will try to create, okay, and let's consider that I have some specific data points like this, okay. So let's say I have some specific data points, something like this, and I have one more data point over here, one more data point over here. Okay, now let's consider this is just for F1 and F2. Now, just by seeing this, because see, I can consider this as one cluster, right? But these two data points are completely different. I may also have some cluster of data points which looks over here. This I'll not consider it as outlier because this is a specific cluster itself. Okay. But when I talk about this particular data point and this particular data point, I definitely can see that, okay, this is a kind of an outlier over here. Okay. Now, what does isolation forest basically say and how we are able to determine this data point as an outlier? Okay. So internally, isolation forest, it will try to create decision trees. Okay. By considering various features, and it will try to split it. And the split will happen in such a way that for every node, for every data points, it will try to go ahead and create a leaf node. Okay. For every data point, right? For every data point, the leaf node will get created. Now, imagine one thing very important over here. Okay. Very important. Let's consider that I have this outlier over here, right? This data point. Now, in order to find out this particular data point, I will also remove this so that I can make your understanding very easy. So by decision tree, what we'll do, we'll try to make a split something like this. Now, as soon as I make a split, I know that I'm able to get one leaf node over here, and this particular leaf node can be for this particular data point, right? Now, this data point is obviously an outlier, right? And for every data point, similarly, we'll try to go ahead and create a leaf node with respect to any number of splits that may happen. Okay. But understand one very important thing is that how we are able to differentiate it with respect to the other points, right? Why I'm not considering this as an outlier, instead I'm considering this as an outlier, because this is an isolation forest. Isolation forest basically means I'm going to make this particular data point completely isolated. Isolated basically means separated, right? Now in this case, in this point, I'm getting this particular point over here. So it is completely isolated as a leaf node. Isolated as a leaf node. Now, why I'm saying this as an outlier? Because I'm able to isolate this data point very much quickly. Just let's say in this case, just in one split, I'm able to isolate when compared to all the other points over here. For all the other points, again, I may go ahead and make a split something like this. I may go ahead and make a split something like this, right? So over here, you can see that the density is also high, and over here, the group of data points will also be available, right? So I'm getting a generic group of data with respect to all the other splits. But in the case of an isolated data point, I'm able to quickly get it. Let's say if another data point is over here, this also I can isolate it by making a split. So this can probably be another leaf node, which can actually belong to this. So this point can also become isolated, right? Now, in order to find an outlier, it is very much simple is that how quickly we are able to isolate them. The path that we are following, in this case it is one path, in this case it is two paths, we are able to isolate both of this data point. And when we are able to isolate this very much quickly, this and this data points are considered as an outliers. How to construct a decision tree and all, we have learnt about it. The entropy, Gini impurity, everything, information gain and all. Now here, I'm specifically not saying decision trees because here we are creating isolated trees. Again, the term over here, I'm going to mention it as isolated trees. Why we are saying it as isolated trees? Because we are isolating this data point. Okay. But how to measure this path and all? For that, a simple mathematical formula is basically given. Okay. And for this, like for every data point, right, we will go ahead and compute the isolation score. Okay. I'll not say isolation score, but I'll just go ahead and compute the anomaly score. Okay. Like if I say that, okay, for this particular data point, what is the anomaly score? Why you are considering that as an outlier? For this data point, what is the isolation score? For this data point, what is the isolation score? And if it crosses a specific threshold, we consider that as an outlier. Very simple. If you know about the decision trees, I think this will be super easy for you all to understand. Okay. Now let's talk about the mathematical formula that we specifically use. Mathematical formula that we specifically use to compute the anomaly score of a new point. So I'll write over here, compute anomaly score for the, so sorry guys, this is anomaly. Okay, it's not anomaly. Sorry about that. It's something written as anomaly. Okay. Sorry for the spelling mistake. This is also anomaly. Okay. Now, how do I compute the anomaly score for a new point? Very simple. If I consider this new point, let's say this new point, I want to consider this new point. I want to go ahead and compute the anomaly score. I want to consider this as a new point. And I want to go ahead and compute the anomaly score. Very much simple. Okay. First of all, the notation that I'm going to write is in this way. S of x comma m. Okay. What is m? I will just talk about it. M over here basically means sample size of the data points. Sample size of the, or I can say number of data points, just simple way. Number of data points. Okay. So this is my m. Okay. Now considering with respect to the x, what is x? X is nothing but for which data point I want to compute the anomaly score. So here I will just write it as data point. Okay. Now this formula is basically given to compute the anomaly score as 2 to the power of minus e to the power of h of x. I will talk about what is h of x divided by c of m. Okay. So it is something like c of m. Okay. C of m. I will talk about this notation, but let's talk about it one by one. Okay. First of all, what is h of x? H of x is nothing but the average search depth for x from the isolated tree. I told you, right? Whenever we are computing, right, what we will compute? The path, how quickly we are able to get to this isolated leaf node. If I'm able to get it in just one depth, like one path, right? So I will just say the depth is only 1, right? Then if I'm able to get the isolated in 2 depths, so I will just go ahead and write 2. So that is what this h of x basically gives. Okay. And e of h of x will be that value where it is basically calculating the average. Okay. So here I will write it as e of h of x. Okay. Then similarly, c of m. What exactly c of m is? It is basically saying average value of h of x, or I can also say average depth of h of x. Now, what is the difference between it? First, I was just computing for only the x data point. What is the depth? Average data point, right? And like this, lot of isolation trees will be created, right? Lot of isolated trees will be getting created, right? If I probably select different features, lot of isolated trees will get created like this. We will just not be dependent on one tree. If I am using isolation forest over here, we will be having many trees. And for every tree, the path may be different for an isolation forest, because based on the features, I can split it and however I want. If I have 4 features, I can start with F3 feature, I can start with F4 feature. Okay. So based on that, multiple different isolated trees will be there. So the first thing, what is the average search depth for X from the isolated tree? So let's say over here it was just 1 path, over here it was 2 path. In the third tree, it can be 4 path, 5 paths, something like that. 5 depth part, I'm saying. Okay. Depth 1, depth 2, depth 3, like that. I will try to calculate the average of all those them, and then I will get the E of x of value, E of h of x value, right? Now, similarly, if I say with respect to every data point over here, right? What will be the depth? Let's say for this particular data point 4 is the depth. For this particular data point 5 is the depth, right? Here we are not going to consider x in C of m. We are going to consider for every data point. So then we will just try to go ahead and calculate the average depth of h of x in all the isolation tree, right? Now, my simple understanding will be that if I'm able to find out the outlier, this E of h of x will obviously be very, very less than C of m, right? So my S of x comma m that I probably calculate, this one, it will be approximately equal to how much? See, if this value is very, very much less than this, so this divided by this will be a very small value, right? And if you probably use 2 to the power of minus of that small value, right, you are actually going to get, like, let's say if it is 2 to the power of minus 0.5 or minus 0.1, minus 0.2, like small values, it will be approximately equal to 1 or very much near to 1. So then we can basically say the anomaly score is very, very good. The anomaly score. So this is what is my anomaly score is. And if it is coming very much near to 1, then we can consider that as an outlier. Obviously, we need to define a threshold. See, let's consider that we define a threshold that anything that comes above 0.5, this threshold can be played off, right, with different value. If it is greater than 0.5, it will be considered an outlier. And we know that if E of H of X is very less than of C of M, then this particular value will be approximately equal to 1. Okay. And vice versa, if this E of H of X is greater than C of M, then my H of X comma M will be approximately equal to 0.5. Okay. Or less than 0.5 also it can be. So then we will just consider that this is a normal data point. And this is how we basically go ahead and probably calculate the isolation forest, right? So this was the entire idea behind anomaly detection. All we are doing is that internally we are creating many isolation trees. The only difference between isolation and decision tree is that in isolation tree, we are isolating each and every data point separately. And it's just we are seeing that how much time or how much depth it is probably taking us to receive or to come to that particular isolated point. And just by using this specific formula, this mathematical formula, we can basically find out whether a data point is outlier or not for a specific problem statement. Okay. Now, let me show you a practical example with respect to the isolation tree. So here is the isolation forest anomaly detection. Now here I have considered a healthcare data. So this data is probably hidden, okay, because of the security issue. Now with respect to these two features that I have, okay, so let me just clear all the outputs so that you will be able to understand it. Okay. Now first of all, I will go ahead and read this healthcare data. Now this healthcare data has two features. Okay. And these two features are specifically talking about some kind of disease. Okay. Every person will not have a disease. Okay. This can be too specific, any body specific, you can see any parameters which will determine that specific disease. Okay. So here I have two specific features over here. Very much simple. Right. Now with respect to this two specific feature, not every person can have a disease, right? Only that outlier things that are probably present, that person can have an disease over there, right? So what we'll do for this particular thing, right? Internally, we'll try to create an isolation forest, multiple isolation forest, and then we'll try to predict. Okay. Now, first of all, if I just go ahead and import matplotlib and just see the data set. So here is how my data set looks like. So here you can see this data points. If it is grouped together, you can say that these all are normal data points. This is basically talking about that specific feature in this data set. You may be thinking, Krish, why it is like that? The data set is designed in that specific way. All this group of points that you will be seeing, right? These are almost normal data points for a normal healthy person, right? And these are outliers looks for the the person may have a disease and all. But out of this all data points also, right, we cannot just come to a conclusion that everybody will probably have a disease or kind of thing, right? So what we will do, we will try to perform anomaly detection. So out of all these data points, which are the kind of outliers that you feel that we can probably have a look onto that specific patient. Okay. So for this, again, if you go to sklearn.ensemble isolation forest, we use this. Please read this. Okay. This is super important. Isolation forest algorithm returns the anomaly score of each sample using the isolation forest algorithm. The isolation forest isolates observation by randomly selecting a feature and then randomly selecting a split value between maximum and minimum values of the selected features, and this recursive partition will happen unless and until we get a terminating node or leaf node. Okay, so this all information is there. Now here you can see it is basically talking about n underscore estimators. There is something like max samples, like how many features I have to probably consider, and one more parameter is something about contamination. Okay. So contamination over here, if we probably go and see, right, the amount of contamination of the data set, that is the proportion of outlier in the data set used when fitting to determine the threshold on the scores of the samples. Okay. If auto, the threshold is determined as in the original paper. If float, the contamination should be in the range of 0,0.5. So we'll try to put the values between 0 to 0.5 to make sure that through this we are also able to provide some threshold value, because above this it will be considered as an outlier. Okay, all those things are considered. So here I've written contamination as 0.1. Let me do it as 0.2. So first of all, I have imported sklearn.ensemble, import isolation forest. And then we have used isolation forest over here. Understand, this is an unsupervised machine learning, okay? Anomaly detection is completely based on unsupervised, okay? So here I've written contamination as 0.2. So anything above 0.2, I will be considering it as a outlier. Then cl.fit of df and cl.predict. And this way I will be able to get my prediction. So some warning will be there. Don't worry about that. So here you can see wherever I'm getting the value as ones, these are basically normal data points. Wherever I'm getting the value as -1, these are basically the outliers, like how we did it in the DBScan, okay? And then I will go ahead and import numpy, and I'll say wherever the prediction is less than 0, just get the index. And here is what is my index, okay? So here I will write it as index outliers, okay? So these are my index over here, okay? So 4th, 20th, 24 index will be there, okay? The next thing is that I'm converting this df.values to an array in X variable. I'm saving it. And here I will just use that same index, and now I will display all my outliers. Now see, lovely, the entire scattered plot will come. Initially my scattered plot was something like this, right? So here, let me write it as index. So let's say initially this was my scattered plot, okay? Now if I copy and paste this line where I'm taking index, 0 feature, first feature, and I'm saying edge color will be red. That basically means whichever will be the outlier, that is basically going to consider as red, okay? And this is what index is basically present, because this is basically considered that are the outliers, right, out of that. So what I will do, I will copy this over here, I will paste it over here so that we can see it. Now here you can see all these points, these are basically considered as an outlier in this specific data point. And just by using anomaly detection, how clearly we are able to isolate them, right? And this is all possible because of the simple decision tree that we have learned, right? And in this video, we're going to understand like how we can perform anomaly detection using DBScan clustering. Now, I've already spoken about DBScan clustering. We have understood the entire theoretical concept. We have understood how does clustering actually happens with respect to DBScan. And the most important factor about DBScan is that it is actually able to create clusters, or it is able to create groups in a non-linear separable data. And that is the power of DBScan clustering. When we are discussing about DBScan clustering, because of this power, wherein you can basically create clusters from a non-linear data, there we will also be able to determine the outliers. And this outliers, if it is important for a specific problem statement, that is basically a kind of an anomaly detection application that we can probably create. So in this video, I'm again going to revise you with respect to their DBScan clustering, whatever things we have actually discussed in the past. When I say in the past, just a couple of sessions back. And along with that, we'll also try to implement a new practical example, okay? And then we'll try to see that how we are able to perform the anomaly detection. So with respect to the DBScan clustering, there are 3 major points that everybody needs to remember. One is the core point, one is the border point, and one is the noise or outlier. Now in this particular problem statement, since we are performing an anomaly detection, this noise or outliers will play a very important role. So finding the noise and outliers in a specific data set is basically distinguishing that particular data point from all the normal points, okay? And then whenever we talk about core points, border points, how do we determine that? I'll talk about that. But one important thing is that it is basically this entire DBScan clustering is applied. It performs well when you have a non-linear clustering data, okay? And there are 2 hyperparameters that we are specifically using. One is minimum points. The other one is epsilon, which is nothing but the radius. Now, whenever we talk about the core point, when do we say a specific point or specific data point is a core point? When the number of data points within this particular radius, within this particular circle, right, should be greater than or equal to minimum number of points. So if the minimum number of points is 4, if I probably see and count over here, combining this point, they are around 5. 1, 2, 3, 4, 5, 6. 6 points. So it is greater than or equal to minimum points, that is 4. So we can basically call this as core point or the red point, okay? And similarly, because this kind of points will be distinguished in my entire data set, we'll try to categorize this into core point, border point, and noise or outlier point. Now coming to the next point, that is called as bordering point. Now, when do we say a specific point is a border point? When the number of data points within the radius will be less than the minimum points, that is 4. Okay. If it is less than this particular minimum points, then I will probably be getting this particular border point. Okay. So over here, you can see it is less than 4. Only 3 points are over here. So we will probably categorize this data point as the border point. Okay. Similarly, coming to the outliers, inside this, there will be no other data points within this particular epsilon radius, within this particular circle. Okay. So whenever we are given this particular data points, we categorize into core, border, and noise. So here also, if you see this particular example, if I'm considering minimum points is equal to 4, we are able to categorize this red point, yellow point, and the blue point. Okay. But in our entire problem statement, we will try to focus on this particular outlier, because this is the point that we really need to find. We are not going to focus more on the core point or the border point. Okay. So if I probably show you an example, some example after we applied a DBScan clustering, see in this particular left-hand side, this is a non-linear clustered data point, right? Here we are able to get 2 clusters, but there are so many outliers. And this outliers data point is my anomalies, right? That is completely different from the normal data points that we specifically have. And similarly, in the right hand side, if you see, there is one image on the left hand side, and here we have actually created a group. This clustering has basically happened with the help of k-means, and this clustering has happened with the help of DBScan. Proper clustering are happening in DBScan, but here you are also able to get the outliers. So this is the main purpose of DBScan clustering. Whatever things we have learned earlier, the same thing. But now let me just go ahead and probably show you a practical example. Okay. So I will just go ahead and clear all the outputs. So over here, and let's see with respect to the DBScan. Now here what we are doing is that I will try to create my own data set, which is completely linearly separable. So for this, I'm going to import a library which is called as make circle. I don't require this make moons, because in the previous example, I'd actually given you with respect to this make moons, which will basically create a non-linear data. And then I've imported DBScan, I've imported matplotlib, and this is my make circles, the data set that I have done. Now, in the next thing is that I'll be using this make circle. The number of samples will be 750. I'm using some factors and some noise. The reason I'm using noise is that because even though I'll try to create a circle, it should have some specific noise. Otherwise, it will just be in one single line. All the points will be there. Okay. So this is my x comma y. When I execute this, I'm getting y. Okay. But I will not use this y. Okay. This y is my output feature, right? But as we suggest, right, I will just be using this x feature, and then we will try to apply the DBScan, and then we will try to find out the outliers. So if I try to plot it with respect to y, see here you can see 2 groups. But DBScan obviously can also find out clusters within this, and it will also be able to find out whether there are any outliers or not. Now I will go ahead and import DBScan. I'll use epsilon as 0.10, and again we'll do fit predict on x. Once we do fit predict on x, I will probably be getting all my clusters group. See over here 1, 1, 1, second cluster, second group, 7th group. Wherever there is a value like -1, see this is -1. This -1 are nothing but these are all the outliers, right? So DBScan is able to distinguish this point that is completely different from the normal point. Okay. So if I go and see dbscan._labels, I will be able to see the same point. Now, if I try to do the scatter with respect to this dbscan.labels, now see, here is where I'm getting so many different clusters, right? So this is my green cluster, this cluster. But the most important thing over here is that you need to distinguish this outliers. See, these are my data points which are outliers. If I probably consider this, these are my outliers. These all data points are on my outliers, right? And that is the importance of this. From all these data points, we are able to distinguish abnormal data points, right? And that is what we are able to do with the help of DBScan. So I hope you are able to understand this super amazing thing. Again, this is a very cool application with respect to the outliers and all. If I try to see the real point, my real data point was just like this. But here, with the help of DBScan and some epsilon value, I can play with epsilon value with respect to different, right? That is a kind of a hyperparameter. But here, yes, with respect to any data points, you will be able to see the outlier. And in this video, we are going to see how we can perform anomaly detection of finding the important outliers using local outlier factor. Now, before we discuss about local outlier factor, this is a very simple technique altogether. I really want to define two important terms. One is the local outlier, and the second one is something called as global outlier. Okay, I'll be talking about these two important terms, and we really need to distinguish this, right? In our previous videos, we have learned about DBScan clustering and how it can basically be used to find out the anomalies. We have also discussed about how we can use isolation forest to determine what are the anomalies, right? Now, in this data set, you can see clearly that I have two clusters of data points, right? Now, in this two cluster of data points, it is very much clear that I have two groups. Now, if I talk about this particular data point, right? You can see that both the data points are near to this particular cluster. So I can basically call both this data point as local outlier. Why? Because it is very much near to a specific cluster. Okay. But if I talk about this specific data point, this is basically a global outlier, right? Why we are saying this as a global outlier? Because this is completely different when compared to this all data points that we have, right? Completely different. Whereas these local outliers are somewhere near with respect to this particular cluster. Now, in order to find out this kind of anomalies, it is very much easy with the help of DBScan or isolation forest, right? Because we isolate those kind of data points. But if I really want to determine this particular points that are the local outliers in a proper way, then I can definitely use something called as local outlier factor. Very simple algorithm. So we basically also say LOF, and we also determine something called as an LOF score. Okay. But the entire funda is very much easy, very much simple. Okay. The concept is very much simple, and internally this entirely uses K nearest neighbor concept. Okay. With the help of K nearest neighbor, what they will try to determine, they will try to determine the local density. Super important term, local density. Now let me talk about this, how this entire local outlier factor works. Let's say I have taken k is equal to 5 as my neighbors, because in k nearest neighbor also we try to find out the k value. Okay. Now what we are going to do, we will give a one point like this point, and we'll try to find out whether this is an outlier or not. Now, if this needs to find out whether it is an outlier or not, what it will do, it will find out the nearest 5 neighboring points. Let's say these are my nearest 5 neighboring points. It will calculate the distance and it will do the average distance and all. Now, after doing this, okay, it will keep that information aside. Then we will go ahead and consider this data points, not outlier, this data point. And then we will observe what is the density with respect to this particular neighboring points. So from here, every point, it will try to calculate the distance between the nearest 5 neighbor points from that particular point. So with that, we will able to get, see, anyhow, when we are calculating the average distance, if the average distance is less, that basically means the density is more. If the distance is more, that basically means the density is less. So this is the funda that we can basically apply. So over here, what we are going to do, we are just going to compare the density from this particular neighboring points to this particular point. Okay. So first thing what we are going to do is that, let's say if I want to check whether this particular point is an outlier or not. So what we'll do, we'll take k is equal to 5 or whatever k value we want. We will try to find out the distance. Okay. Then we'll take all the neighboring points. And then with respect to k is equal to 5, we'll try to find out whether the density is more over here or more over here. If the density is less over here, then this can be considered as an outlier. Now, when I say outlier, I'm talking about local outlier. Okay. Again, let me repeat it. So let's say if this is my data point, I will try to find out the k nearest data point. So let's say this is my k nearest data point. Over here, we have calculated the average difference, right? Average distance. If the distance is more, that basically means the density is less, because from this particular neighboring points, if I try to compare all these data points, these are near, right? So the distance will be less, but the density will be more because there are so many data points nearby, right? We are just going to compare the local density, whether the local density is high over here or high over here. You know, in this scenario, since there are many data points, it will be high over here. So this can be considered as an outlier. So this is the entire funda behind local outlier factor. Now, this was about the theoretical intuition. I really want to give you one task, guys, because I have not given you task with respect to any machine learning algorithm. So, local outlier factor is already available in sklearn. We will read this, okay? Unsupervised outlier detection using the local outlier factor. Now, see, every line that I read, you will be able to understand it. So, please let me read it. I've already explained you the theoretical intuition. The anomaly score of each sample is called the local outlier factor. It measures the local deviation of a density of a given sample with respect to its neighbor. It's okay if you have not understood this line also, because next you will be able to understand. It is local in the anomaly score depends on how isolated the object is with respect to the surrounding neighbor. Now, in this particular case, if I see, these particular points are completely isolated, right? This point is also isolated, this point is also isolated, right? How well they are isolated. More precisely, locality is given by k nearest neighbor, whose distance is used to estimate the local density. Okay. Now, this is super important. By comparing the local density of a sample to the local densities of its neighbors. This is the most important line in this paragraph. By comparing the local density of a sample to the local density of its neighbor, one can identify samples that have a substantially lower density than their neighbors. Just by comparing it, one can identify the samples that have a substantially lower density than the neighbors. These are considered as outliers. Again, everything is same. We are using k nearest neighbor. So here you have n underscore neighbor. The algorithm, you can see ball tree, KD tree, brute, auto, everything is discussed. I've already discussed all the theoretical mathematical intuition. Then you have this matrix Minkowski, like which parameter, like Euclidean distance, you want to use a Manhattan distance. Okay. So take a specific data set like this DBScan data set, okay, and just try to apply this local outlier factor. This will be a task for you. At least now, guys, you have learned machine learning. You know about non-supervised machine learning. We have seen so many different problem statements. I feel you should be able to do it now. Okay. So yes, this was it from my side. I hope you like this particular video. I will see you all in the next video. Thank you. Take care.